imagine trying to fly a 200-kilogram bomb from New York to Miami,
Right.
but you're using a lawnmower engine,
Oh.
and not even a good one, like one that intentionally destroys itself after 5 hours.
Yeah, literally running itself to death.
Exactly. And the whole time, it's navigating with the exact same cheap microchip that's sitting inside your smartphone right now.
It sounds completely absurd when you put it like that.
It really does. But I mean, welcome to the uncompromising world of modern UAV engineering. You know, when we normally look at vehicle engineering like civilian stuff, we're looking at the art of compromise.
Oh, absolutely. It's all about balance.
Yeah. Like a consumer car is this careful balance of aerodynamic efficiency, keeping the cabin quiet, having enough trunk space, and, enough torque to actually merge onto a highway without causing a pileup.
Right. You're always trading one metric to slightly improve another. But you can't break the overall harmony of a machine. The consumer market demands that equilibrium. Because, I mean, think about it. If you drop a highly specialized, ultra high-stress drag racing engine into, like, a family minivan,
That would be terrifying.
right, it creates this undrivable, deafening nightmare for the passengers. And on the flip side, if you put a low-emission eco-motor into a Formula One car, well, you're guaranteed to lose the race.
You'd get lapped on the first turn.
Exactly. Civilian engineering is anchored in livability. It has to do multiple things well.
Which is precisely why the design landscape of uncrewed aerial vehicles drones is just so jarring to look at.
It's a completely different paradigm.
Yeah, because the second you remove the human occupant, the need for that equilibrium just completely evaporates. We're looking at a space defined by ruthless, extreme optimization.
You basically abandon every secondary function.
Every comfort, every safety margin,
All gone?
just to achieve one highly specific tactical goal.
And it forces engineers to operate at the extreme bleeding edges of thermodynamics and material science. Because the foundational rule here is, well, it's the physical impossibility of having it all.
You just can't.
No, you cannot design a platform that has intercontinental range, absolute silence, and microscopic manufacturing costs simultaneously. It defies physics.
If you want to push one of those vectors to the max, you have to violently sacrifice the others.
Exactly.
And that harsh physical reality, that is the mission of our deep dive today. We're decoding the hidden heart of modern UAVs, which is their power architectures.
The engines, the batteries, the fuel cells.
We're going to explore how the physical propulsion system of a drone strictly dictates its tactical destiny. And we've got an incredibly extensive stack of source material to guide us today.
Really good stuff in this stack.
Yeah, it's dense. We're pulling from highly detailed defense engineering specifications, academic papers on thermodynamic hybrid systems, leaked technical manuals like the DR-02 and DR-05 documents.
Those are fascinating, by the way.
Oh, they're gold mines. Plus, we've got on-the-ground battlefield forensic reporting from outlets like Euromed and Press and New Atlas.
And the value of this specific stack of documents is that it completely bypasses the, superficial strategic commentary. We're not looking at high-level politics here.
No, right.
These sources take us directly into the circuit boards, the structural blueprints, the fuel consumption math that actually governs reality on the battlefield.
Right. And before we start unpacking those blueprints, I do want to frame this really clearly for you listening. The sources we're using extensively detail tech that is actively deployed right now in the ongoing Russo-Ukrainian war.
Right. So we're talking Russian, Ukrainian, Iranian engineering.
Exactly. And we are examining all of this strictly through an impartial, technical lens.
Purely the engineering.
Yes, we're focusing entirely on the logic, the physics, and the hardware trade-offs without taking any political sides. We are solely interested in the applied science of how these machines operate under extreme conditions.
And to understand that science, we have to look at the extremes. We're going to trace the evolution from the loudest, most brute force combustion engines all the way to the absolute bleeding edge of silent hydrogen tech.
So let's start at the extreme end of the scale for sheer distance and payload. We're looking at what I like to call the engine of attrition.
The Shahed 136.
Right. Also heavily utilized under the Russian designation, the Geran-2. This thing establishes our baseline for how internal combustion is weaponized for sheer strategic reach. It's a heavy loitering munition.
Very heavy. Weighs roughly 200 kilograms at takeoff.
Yeah, that's massive for a drone. And it's engineered for a staggering operational range. We're talking 350 to 2,500 kilometers.
Which is wild. And when a platform requires that magnitude of distance combined with a heavy kinetic payload, a big bomb, The energy density of liquid fuel just remains unmatched.
You can't do that with batteries.
Not even close. So internal combustion becomes the only viable architecture. The Shaheed relies on a very specific power plant known as the Mato MD550 engine.
And looking at the technical manuals, they identify the MD550 as a reverse-engineered clone of a German engine, right?
Oh, yeah.
The Limbach L550E,
That's the one.
which is so weird to me because the Limbach was originally designed in the late 1980s for this incredibly narrow civilian application motor gliders.
Right, just cruising around on a Sunday.
Exactly. It's a 548cc, four-cylinder, two-stroke engine, puts out roughly 50 horsepower. But what immediately stands out when you look at the schematics is the physical geometry of this engine. It uses what's called a horizontally opposed layout.
A boxer engine.
Yeah, boxer. Why is that specific shape so important?
Oh, the physical layout is basically the keystone to the entire platform's viability. So think about a standard inline engine like you'd find in a motorcycle.
Okay, where the pistons go up and down in a line.
Right. That directional mass moving vertically creates significant shaking forces. The engine block inherently wants to vibrate up and down violently, but in a boxer engine, the cylinders are laid flat.
They're horizontal.
Exactly, oriented 180 degrees away from each other on opposite sides of the crankshaft. So when the stock plugs fire, the opposing pistons punch outward at the exact same time and then pull inward at the exact same time.
So the best analogy I can think of for you listening is imagine two people of the exact same size and strength pushing on opposite sides of a revolving door at the exact same time.
That's a perfect way to visualize it.
Right. A massive amount of force is being exerted, but because the forces are perfectly opposed, the central axis of the door doesn't shift at all. The pistons are physically boxing against each other's momentum.
Which is why they call it a boxer engine. And that perfectly opposed momentum cancels out what mechanical engineers call first-order vibrations. For a two-stroke engine of this size, it runs shockingly smooth.
So the engine block stays stable.
Highly stable. Which minimizes structural fatigue on the airframe, sure, but that's not the real reason they chose it.
Right, because the sources point out this direct correlation between the Boxer's low vibration and the electronics they use for navigation.
This is where the extreme optimization comes in. To fly 2,000 kilometers, a military platform normally needs highly sophisticated, million-dollar ring laser gyroscopes.
Military-grade hardware.
Exactly. But the Shaheed abandons all of that for commercial-grade MEMS IMUs.
Okay, let's break those acronyms down. MEMS means microelectromechanical systems, and IMU is inertial measurement unit. And the forensic reports note these are basically functionally identical to the accelerometers and gyroscopes manufactured for consumer smartphones.
Literally the same chips that tell your phone to flip the screen when you turn it sideways.
That is insane. How does that even work in a missile?
Well, a MEMS gyroscope has these microscopic silicon structures inside it, often shaped like tiny tuning forks etched right onto the microchip. When you apply a voltage, they continuously vibrate.
Okay.
If the drone rotates, the Coriolis force causes these vibrating silicon masses to deflect slightly. Microscopic capacitors detect that deflection, and the software calculates how fast the drone is turning.
But the vulnerability there seems glaring. You have microscopic, physically vibrating silicon tuning forks trying to measure delicate forces. If you bolt that to an engine that's violently shaking,
it introduces massive mechanical noise. If the engine's vibration frequency happens to match the resonant frequency of those tiny silicon tuning forks, the sensor gets completely saturated.
it just overloads.
The signal-to-noise ratio completely collapses. The IMU essentially experiences vertigo, it loses its spatial orientation, and the drone will inevitably dive straight into the dirt.
So by using the naturally balanced geometry of the Boxer engine, the vibration is suppressed just enough to allow these cheap, mass-produced microchips to actually function over thousands of kilometers.
The engine shape literally dictates the supply chain of the microchips.
That is fascinating. The hardware dictates the software. And that brings us to this wild evolution detailed in the forensic reports. So the Iranian MD550 was already a cheap engine, but the localized Russian variant, the Juran 2, takes cost optimization to this ruthless extreme.
Oh, the teardowns on the Juran 2 are wild.
They actively removed the starter motor and the flywheel from the engine block, just gone.
Just to save weight and reduce manufacturing costs.
Which introduces this concept we should probably categorize as extreme lifespan optimization.
Right. Because a commercial car engine is built with metallurgy, meant to endure friction for hundreds of thousands of miles over decades.
It's meant to last.
A loitering munition fundamentally only needs to operate for 4 to 5 hours before detonating upon its target. Every ounce of metal dedicated to long-term durability is just wasted mass.
It's the ultimate disposable machine. But wait, by removing the starter motor, they're acknowledging the engine never actually needs to start while it's sitting on the ground, right?
Exactly. Launching mechanics replace the onboard starter.
So how does it start?
The drone is launched using a solid propellant rocket booster, usually off a rail or a truck bed. That booster violently accelerates the drone into the sky. Once it hits a certain airspeed, the kinetic force of the ambient air ramming against the wooden propeller forces the crankshaft to rotate.
So the wind physically turns the engine over.
Yes, it's called windmilling. The wind spins the prop, which turns the engine over until the spark plugs ignite the fuel mixture, and boom, it sustains its own combustion cycle.
So they've basically built an aerodynamic shell, wrapped it around a flying gas tank, powered it with a disposable lawnmower engine that needs a literal rocket just to turn on.
That's a very accurate summary, yes.
And because it's a two-stroke, it has this incredibly loud, grating acoustic signature. The battlefield nickname for it is literally the moped.
Because it sounds exactly like a broken moped flying overhead.
Right. So if it doesn't have radar-absorbing coatings, it doesn't have fancy terrain-following radar, and it loudly advertises its approach from miles away.
How is it so tactically effective?
The math. The efficacy is rooted entirely in economic asymmetry, driven by what we call the fuel mass fraction.
Break that down. So out of its 200-kilogram maximum takeoff weight, about 150 to 160 liters is just liquid fuel. Because they excised all the complex avionics, the heavy starter motors, the expensive optics, the unit cost plummets, it's estimated to be somewhere between $20,000 and $50,000.
Which is pocket change in military terms.
Exactly. The tactic relies on economic exhaustion, not stealth. It's pure saturation. You launch 30 or 40 of these at once. The defending forces will absolutely detect them on radar, on acoustic mics, everything.
You know, they're coming.
But engaging a $30,000 drone with a modern surface-to-air interceptor missile that costs, say, $1.5 million, that creates a completely unsustainable kinetic exchange ratio.
You go bankrupt defending yourself.
The loud, unrefined engine provides the cheap distance necessary to force the adversary to continuously deplete their high-value air defense stockpiles.
Okay, so the internal combustion engine in the Shaheed is optimized for sheer expendable distance. But battlefield requirements aren't just one thing. What if a commander has a totally different mission?
Right, different mission, different architecture.
Say they don't want to fly 2,000 kilometers to blow up. Say they need a drone to orbit a specific operational sector for an entire day, maintaining a persistent data link, capturing high-res artillery correction imagery, and then returning to base to be refueled for tomorrow.
A completely different set of parameters.
And those parameters render the Shaheed's power architecture entirely useless, right?
Completely useless. A high vibration, disposable, acoustically deafening two-stroke engine cannot serve as a stable platform for delicate optical sensors. And it definitely doesn't have the fuel efficiency to loiter in one area for 16 hours.
Which necessitates a radical shift in how we harness chemical energy. That moves us to the second platform in our stack of sources, the Orlan 10.
A fascinating piece of machinery.
Visually and mechanically, it's a massive departure. The Orlan is a tactical reconnaissance UAV. It's much smaller, weighing roughly 14 to 18 kilograms. And instead of that massive boxer engine, it relies on a micro, single-cylinder, four-stroke engine.
Specifically modeled on platforms like the Saito FA-62B, it produces just under a single horsepower.
1 horsepower. Yet the endurance metrics are staggering. With a tiny fuel tank, it's rated for 16 to 18 hours of continuous flight.
Almost a full day. To achieve that on a micro-engine, you have to really dig into the thermodynamics of combustion cycles. We have to dissect the mechanical divergence between the two-stroke cycle of the Shaheed and the four-stroke cycle of the Orlan.
Okay, let's trace the flow of fuel and air. Because the fundamental issue with a two-stroke engine is how it manages the intake and exhaust phases at the exact same time, right?
To generate power on every single downward stroke of the piston.
So how does that work in the Shaheed?
In a standard two-stroke, as the piston gets forced down by the explosion, it simultaneously uncovers an exhaust port in the cylinder wall while also pressurizing the crankcase below it.
Okay.
That pressure forces a fresh mixture of air and fuel up through a transfer port and into the combustion chamber. And this fresh, pressurized mixture physically rams the spent exhaust gases out of the open exhaust port,
Like pushing old water out of a pipe with new water.
Exactly. This fluid dynamic process is called scavenging.
But the thermodynamic flaw there is unavoidable overlap, right? Because both the intake and exhaust ports are open at the exact same time for a fraction of a second, a significant percentage of your unburned, perfectly viable fuel gets blown straight out the exhaust pipe.
Along with the spent gases, yeah. You are literally dumping unignited energy straight into the atmosphere.
Which seems terribly inefficient.
It is. It guarantees a high power-to-weight ratio because it fires twice as often as a four-stroke, but it severely punishes the brake's-specific fuel consumption, or BSFC.
Meaning it guzzles gas.
Exactly. Now, the Orland's micro four-stroke engine physically separates these fluid dynamics into dedicated, independent mechanical phases.
Intake, compression, combustion, and exhaust.
Right. During the four-stroke exhaust phase, the piston travels upward, physically pushing the spent gases out through a dedicated, mechanically timed exhaust valve. The intake valve remains completely closed.
So no fresh fuel sneaking out.
None. Only when the exhaust valve shuts does the intake valve open to draw in the fresh mixture.
So by isolating those phases, the four-stroke cycle virtually eliminates that scavenging loss.
Which reduces the specific fuel consumption by over 40% compared to a two-stroke engine of the exact same size.
40%? That's massive.
It is. If your operational requirement is to keep an 18-kilogram airframe aloft for 16 hours using a fuel tank smaller than a standard jerrycan, the four-stroke Otto cycle is literally the only thermodynamic path that complies with the laws of physics.
Okay, so the efficiency of the combustion cycle dictates the endurance. But the sources also highlight that this tiny 1-horsepower engine is managing an intense division of labor, because a tactical recon drone isn't just a glider, it's basically an airborne server rack.
It's hauling a lot of heavy electronics.
Yeah, the payload specs for the Orlan 10 include active electronic warfare jamming modules, cellular network interception rigs, advanced multispectral optical gimbals. All of that requires serious electricity.
And if you tried to power those active payloads for 16 hours using lithium-ion batteries,
Batteries would weigh too much, right?
no, they would easily exceed the drone's maximum takeoff weight. The drone wouldn't even get off the ground. So the engineering solution here is physical power coupling.
Explain that.
The micro four-stroke engine's output shaft isn't just dedicated to spinning the propeller, it's mechanically linked to a lightweight, high-output alternator.
Oh, so it's a generator.
Exactly. The engine acts as a continuous airborne power plant, dynamically converting chemical hydrocarbons into the electrical current required to keep the jamming modules and thermal optics active for the entire duration of the flight.
So it's efficient, it generates its own electrical power, but we also have to talk about how rugged this thing is. Because the Orlan is designed for austere environments. It doesn't use paved runways.
No, you're launching this from a field or a dirt road.
Right. The launch telemetry shows it's fired from a collapsible catapult.
And the physical stress of a catapult launch on an internal combustion engine is immense.
How bad is it?
The acceleration imparts upwards of 10 Gs of axial force on the airframe. The engine's internal components, the crankshaft, the bearings, the connecting rod, are suddenly subjected to 10 times the force of gravity, trying to rip them backward through the engine block, all while they are actively spinning at thousands of revolutions per minute.
That sounds like it should just rip the engine apart.
It would if it weren't reinforced. And the recovery sequence is equally violent. The drone cuts its engine, deploys a parachute, and physically slams into the dirt.
No landing gear at all.
None. There is no landing gear to absorb the kinetic energy. So the metallurgical specifications for the Orlan's engine components have to reflect this repeated trauma.
Right, because if they just used standard hobby-grade aluminum.
The sheer radial load during the catapult launch, combined with the blunt force trauma of the parachute impact, would introduce microfractures along the engine block.
And those cracks would just grow over time.
Exactly. Over successive flights, these microcracks would propagate, leading to catastrophic structural failure. You'd lose all your oil pressure mid-flight. So the engine block, the valvetrain housing, and the alternator coupling are extensively reinforced to survive this specific ballistic cycle.
Add to that the environmental tolerances. The technical manuals explicitly require cold start capabilities at negative 30 degrees Celsius.
Which is brutal for oil viscosity and fuel atomization.
So it's an absolute marvel of ruggedized endurance. However, the thermodynamic reality of internal combustion introduces an insurmountable tactical flaw. If the engine is constantly running for 16 hours, converting chemical explosions into mechanical motion, it is inevitably broadcasting its position, right?
You can't hide combustion. It fundamentally relies on the rapid expansion of heated gases. You cannot contain the entirety of that thermal energy.
Even if you try to cool the exhaust.
Even with low heat exhaust routing, where they direct the exhaust pipe over the wing surfaces to mix it with ambient airflow and dilute the temperature, the engine block itself still becomes a localized heat source.
And against an adversary equipped with modern thermal optics or infrared-guided interceptors.
A hot engine block against the cold upper atmosphere operates like a flare. It's a glowing beacon.
Plus the acoustic noise. It's quieter than the Shaheed, sure, but acoustic microphone arrays can still hear it.
Easily. So when the mission profile shifts from wide area observation to surgical, undetected interdiction, the thermal and acoustic emissions of internal combustion become an unacceptable liability.
You just can't be stealthy with a gas engine.
No. To achieve true battlefield stealth, you have to eliminate the combustion cycle entirely. You must pivot to pure electromagnetism.
Which leads us directly into our third platform, the silent assassin of the modern battlefield, the Lancet 3.
This is a masterclass in exploiting electric propulsion for lethal effect.
It really is. It weighs roughly 12 kilograms, carries a 3-kilogram high-explosive anti-tank warhead, and it abandons liquid fuel completely. The power architecture is centered on a high-torque, electric brushless motor.
Teardowns identify it as the AXI-5330.
Paired with this incredibly distinctive dual X-wing aerodynamic layout.
The Lancet 3 serves as the direct counterpoint to the Shaheed. Where the Shaheed leverages mass, noise, and distance, the Lancet leverages absolute silence, precise loitering, and sudden terminal velocity.
Let's dissect the physical signatures that make the electric motor so lethal here. The primary advantage is the near-total elimination of acoustic warning, because an electric motor doesn't rely on percussive explosions.
Right. The acoustic profile of a high-end brushless motor is essentially limited to the aerodynamic shear of the propeller blades cutting through the air and a faint electromagnetic whine.
And in a tactical environment filled with ambient noise wind, vehicle engines, distant artillery, the acoustic signature of the Lancet is effectively zero until it is within the final seconds of its terminal dive.
By the time the target registers the sound of the propeller, it is mathematically too late to initiate evasive maneuvers or deploy countermeasures.
But even more critical than the acoustic stealth is the thermal evasion. Modern armored columns rely heavily on FLIR, forward-looking infrared, to scan the sky for threats.
And because the Lancet lacks a combustion chamber, it has no exhaust manifold, no radiator. Its thermal delta relative to the surrounding environment is incredibly narrow.
It just doesn't get hot.
An electric motor operates at a fraction of the temperature of an internal combustion engine. The heat generated is primarily due to the internal resistance of the copper windings and the battery cells.
And the sources say the composite fuselage acts as a thermal insulator.
Exactly. So on a thermal camera, instead of appearing as a glowing white-hot beacon, the drone blends seamlessly into the ambient background radiation of the sky or the ground clutter. It effectively renders standard thermal early warning systems blind.
But achieving this level of smooth, quiet power delivery isn't just about bolting a battery to a motor. The sources spend a lot of time detailing the avionics that control the power flow, specifically the electronic speed controllers, the ESCs, and their use of FOC algorithms.
This is crucial. We need to clearly define how FOC fundamentally changes the motor's performance.
Right. FOC stands for Field-Oriented Control.
To appreciate its impact, we must contrast it with legacy electronic speed controllers. Older ESCs managed motor speed using a method called block commutation.
Which did what?
It basically sent power to the motor windings in abrupt square-wave pulses. The controller was violently turning the electromagnets completely on and then completely off in rapid succession.
Just hammering the motor with power.
Exactly. That square-wave power delivery is highly inefficient and creates intense micro-vibrations in the stator.
Which is what causes that high-pitched abrasive whining sound you hear on cheaper consumer drones.
Exactly. The square wave is electrically noisy and mechanically harsh. FOC revolutionizes this by utilizing a dedicated 32-bit microprocessor to perform complex vector mathematics in real time.
Like what kind of math?
Specifically, it uses mathematical transformations, like the Clark and Park transforms, to monitor the exact rotational position of the motor's rotor and then continuously adjust the electrical current to maintain the magnetic flux at a precise 90-degree angle to the permanent magnets.
So instead of a violent on-off square wave, The FOC controller modules the power into a perfectly smooth, continuously flowing sine wave.
And the application of a pure sine wave yields cascading tactical benefits. First, it eliminates the electromagnetic torque ripple.
Which silences the whine.
Completely silences the high-pitched mechanical whine. Second, it drastically reduces electromagnetic interference, or EMI. High-frequency square waves broadcast electromagnetic noise that can actually interfere with the drone's own onboard GPS and optical sensors.
You don't want to jam your own drone.
Exactly. FOC keeps the electrical environment pristine. And finally, this smooth commutation increases the overall thermodynamic efficiency of the motor by 10 to 20%.
Which is huge when you're on limited battery.
It allows the drone to extract every possible second of flight time from its lithium cells.
And the electric architecture doesn't just enable stealth. It enables a terrifying terminal phase. The X-shaped wings provide extreme pitch and roll authority, and the sources say this thing can execute terminal dives at speeds exceeding 300 kilometers per hour.
Which is heavily reliant on the specific torque characteristics of an electric motor. The torque curve of an electric motor is fundamentally different from internal combustion.
Right, because an engine needs time to spool up.
Exactly. The rotational mass of the crankshaft has to accelerate through its RPM range to reach peak power. But a brushless electric motor possesses maximum torque at 0 RPM.
It's absolute instantaneous power delivery. The moment the flight controller demands full throttle, maximum magnetic force is applied to the prop instantly.
And this instantaneous torque is weaponized when paired with the onboard targeting systems. The sources identify the Lancet's optical tracking system as being driven by edge computing processors, specifically mentioning the NVIDIA Jetson TX2 architecture.
So it's using AI to track targets.
Right. When this AI-driven optical lock identifies a moving target, say a mobile radar system attempting to relocate, the flight controller can instantly dump maximum amperage into the motor, violently adjusting its trajectory and accelerating into that 300 km per hour dive.
The sources even mention a tactic evolving from this extreme agility known as air mining. Have you seen this?
Oh, where they use it air to air.
Yeah. The instant acceleration and precision of the electric motor are used to rapidly intercept and physically ram slower, larger reconnaissance drones midair. They're effectively using a loitering munition as a localized kinetic anti-air missile.
It is the ultimate expression of electric stealth and agility. However, the reliance on lithium-ion or lithium polymer chemistry introduces the unavoidable bottleneck of energy density.
Which brings us to the fatal flaw of pure electric platforms. The Lancet, for all its terrifying stealth and instantaneous torque, is severely restricted by range anxiety.
Just like an early electric car.
Exactly. The operational flight time is strictly capped at roughly 40 minutes. The lithium chemistry simply cannot store enough electrons to maintain sustained flight beyond that window without making the airframe too heavy to fly.
You are confronted with a rigid engineering paradox here.
You can have the internal combustion of the Orlan, which gives you 16 hours of persistent endurance, but it broadcasts your position to the entire theater.
Right.
Or you can have the electric motor of the Lancet, which provides perfect thermal and acoustic cloaking, but forces you into a highly compressed 40-minute operational window.
So the ultimate holy grail of UAV engineering is bridging this gap. How do you design a platform that possesses the 16-hour persistence of a gas engine, but maintains the silent, cold-running stealth of an electric motor?
And the sources reveal that engineers are aggressively pushing into a radical hybrid power architecture to solve this exact problem.
We are witnessing the transition away from both traditional combustion and conventional lithium batteries. We're entering the realm of electrochemical generation.
This brings us to platform number 4, the Raybird. Developed by a Ukrainian aerospace firm called Skyton, this is a deep reconnaissance platform that was originally built around a standard internal combustion engine.
But the engineering data details an active, highly sophisticated refit, transitioning it into a hydrogen fuel cell hybrid system.
And the specifications are incredibly ambitious. We're looking at a 23-kilogram maximum takeoff weight, aiming to achieve 12 to 20 hours of continuous flight time utilizing electric propulsion.
To achieve that duration using electric motors, the power architecture must dynamically manage energy generation and energy buffering.
Break down the primary power plant for us.
The Raybird relies on a primary power plant consisting of a 2-kilowatt proton exchange membrane fuel cell, or PEMFC, and that is paired with a secondary, high-discharge 12-cell lithium polymer battery pack.
Okay, the internal chemistry of the proton exchange membrane is the core of this endurance. We need to clearly explain how this unit extracts electricity from hydrogen gas without any combustion taking place, because nothing is burning here, right?
Yeah. Nothing is burning. The PEMFC is a marvel of electrochemical engineering. The cell consists of an anode and a cathode, separated by a specialized polymer electrolyte membrane.
Oh.
Hydrogen gas is pumped into the anode side. At the anode, a platinum catalyst physically strips the electrons away from the hydrogen molecules.
Leaving just the positively charged protons.
Exactly. And the membrane acts as a molecular bouncer. It allows the positively charged hydrogen protons to pass directly through it to the cathode side, but it absolutely blocks the negatively charged electrons.
So the electrons are trapped on one side.
Right. Because they cannot pass through the membrane, they are forced to travel along an external circuit wire to reach the cathode.
Ah, and that forced movement of electrons through the wire is the electrical current.
Exactly. That is the current that powers the drones, motors, and avionics. When those electrons finally reach the cathode, they reunite with the hydrogen protons and atmospheric oxygen to form the only byproduct of the entire reaction.
Pure water vapor.
Just water. There are no moving parts in the generation process, no explosions, and almost no heat. The fuel cell provides an incredibly efficient, continuous, and steady flow of electricity, making it perfect for maintaining cruising altitude for 20 hours.
But the fuel cell has a critical vulnerability regarding dynamic flight, doesn't it?
It does. Fuel cells suffer from poor transient response. The electrochemical reaction takes time to scale up or down.
So if you suddenly need a lot of power,
Say the drone is hit by a violent thermal downdraft, and the autopilot demands an immediate spike in power to the motors to maintain altitude. The fuel cell simply cannot accelerate the hydrogen flow fast enough to meet that instantaneous electrical demand.
the voltage will sag.
The voltage drops, and the drone could stall and crash.
Which is exactly why the hybrid architecture is mandatory. The continuous, steady output of the fuel cell must be dynamically balanced with a system capable of violent energy delivery.
This is where the secondary lithium polymer, or LiPo, battery is integrated. The electrical architecture connects the fuel cell and the battery via a highly advanced bidirectional DC-DC converter.
Okay, what does that converter do?
During normal cruising flight, the fuel cell easily provides the required wattage, and the DC-DC converter routes any excess power to keep the secondary LiPo battery at a 100% charge. It acts as a high-speed energy traffic controller.
Because a fuel cell's output voltage naturally fluctuates, right?
Based on the load, yes. But the flight controller and motors require a stable, constant voltage to operate smoothly. So the DC-DC converter uses high-frequency switching circuits to dynamically step up or step down the fuel cell's voltage thousands of times per second, matching it perfectly to the battery's voltage bus.
And when the drone requires a sudden, massive burst of power light during takeoff, or navigating heavy turbulence.
The flight controller instantly draws the required high amperage current directly from the LiPo battery. The battery acts as a high-speed energy buffer, providing the instant torque the fuel cell lacks.
And once the maneuver is done,
Once the power demand drops, the fuel cell smoothly takes over the primary load again and recharges the battery for the next event.
the tactical ramifications of this hybrid system are profound. According to analysis from ZME Science, the Ray Bird achieves a negligible heat signature. Because the primary waste product is water vapor and low-grade heat, the drone can penetrate deep into hostile radar-contested airspace without illuminating infrared early warning systems.
It successfully combines the 20-hour loiter time of the Orlan with the acoustic and thermal invisibility of the Lancet.
It allows a commander to establish a persistent, virtually undetectable observation node deep behind enemy lines, monitoring logistics for an entire day without refueling. But
There's always a but.
always. The physical reality of utilizing hydrogen introduces severe engineering and logistical friction. Managing hydrogen gas is arguably the most difficult aspect of this entire platform.
It's the lightest, least dense element in the universe. It actively resists being contained.
Right. If you want to store enough hydrogen on a 23-kilogram drone to fly for 20 hours, you can't just pour it into a plastic wing tank like gasoline.
No, to achieve the necessary volumetric energy density, the hydrogen must be aggressively compressed. The technical specifications indicate the use of specialized pressure vessels rated for 300 bar.
And just to contextualize 300 bar for you listening, That is approximately 4,350 pounds per square inch of outward pressure constantly trying to rupture the tank.
It's basically a bomb if it fails. Containing that immense hoop stress requires highly specialized composite overwrapped pressure vessels, or COPVs.
What are those made of?
They typically utilize an impermeable aluminum inner liner wrapped in multiple layers of high-tensile carbon fiber set in epoxy resin. They are incredibly strong, but they're also very bulky.
So bulky that the engineers at Skyton were forced to completely redesign the fuselage of the standard Raybird explicitly to manage the sheer volume and structural mounting requirements of these high-pressure cylinders.
Right, ensuring the center of gravity remains stable as the hydrogen mass depleted over the 20-hour flight.
And beyond the airframe itself, the logistical tail required to support a hydrogen drone in an austere combat zone is just massive. A frontline infantry unit cannot siphon hydrogen out of a supply truck's fuel tank.
No, the supply chain requires operators to either transport and swap out heavy, pre-filled, pressurized hydrogen cartridges, which must be manufactured and shipped from centralized facilities, or deploy mobile on-site hydrogen generators.
And those generators rely on electrolysis to crack water into hydrogen and oxygen, which means the operators now require a dedicated supply of purified water and a massive external power source just to refuel the drone in the field.
It is the absolute pinnacle of sophisticated, long-endurance stealth, but it introduces a fragile, highly complex logistical footprint that requires dedicated, specialized personnel to maintain.
Which introduces a completely valid tactical pushback. The Raybird is an engineering marvel for deep strategic reconnaissance. But consider a frontline trench unit actively engaged in close-quarters combat.
They don't care about a 20-hour loiter time.
Exactly. Nor do they have the logistical capacity to manage 300-bar hydrogen tanks.
No.
Their tactical requirement is absolute, raw, instantaneous explosive power to punch through a reinforced bunker or heavy armor in the next 5 minutes.
When the mission profile demands immediate kinetic destruction at close range, you discard endurance, you discard complex hybrid energy management, and you strip the power architecture down to maximize one specific metric: extreme electrical discharge.
This takes us to the absolute opposite end of the electric spectrum, and the final platform in our deep dive, the Mammoth Heavy FPV.
If the Raybird is a delicate, highly complex endurance glider, the Mammoth is a purely violent, high-torque drag racer.
Developed by a Ukrainian collective known as Eskadron, this is a heavy-lift, first-person view quadcopter. It exemplifies the philosophy of the glass cannon perfectly.
It really does. It's constructed from relatively cheap carbon fiber plates and commercially available motors, bringing the unit cost to a remarkably low $700.
$700.
But its defining characteristic is its payload capacity. It is engineered to carry a massive 4-kilogram warhead.
And the sources emphasize that a 4-kilogram payload is effectively double the capacity of standard market FPV drones. We are talking about strapping a full-size thermobaric warhead or a heavy tandem-charge anti-tank grenade to a small plastic quadcopter.
But the engineering trade-off is severe. The maximum flight time is drastically compressed to between 3 and 10 minutes.
That 3 to 10-minute window perfectly encapsulates the entire theme of extreme engineering trade-offs we've been talking about. The designers intentionally sacrificed longevity.
The platform does not need to linger for 20 hours. It doesn't need the 40-minute hunting window of the Lancet. It only requires a few minutes of terrifying, unstoppable kinetic momentum to close the distance between the trench line and the target.
But how does the internal chemistry of a $700 drone generate the sheer torque required to lift a 4-kilogram block of explosives and still maintain the agility to fly at 60 miles per hour while dodging incoming fire?
The secret lies entirely within the specific battery cell chemistry. The engineering sources identify the power source as utilizing premium lithium-ion cells, specifically the Molicel P50B and P45B in the 21700 form factor.
Okay, to understand why these specific cells are chosen, we have to look at how battery engineers balance capacity versus discharge. In a lithium-ion cell, you're constantly fighting internal resistance, right?
Always. If you design the cell's internal structure to hold a massive amount of energy for a long time, high capacity, the internal resistance naturally rises.
And high internal resistance means you cannot pull the energy out quickly without the battery overheating.
Right. But the Molicel P50B cells are engineered with highly conductive internal materials, minimizing that internal resistance. This allows them to achieve extreme post-discharge rates. The specifications show these cells can support up to 100 amps of pulse discharge.
To put 100 amps into perspective for the listener, drawing that much current through a circuit is enough electrical flow to power a heavy-duty industrial welding machine.
Pushing that much amperage through a small lithium-ion cell creates intense thermal stress.
Because the math dictates that power loss as heat equals the current squared multiplied by the resistance.
Exactly. Even with the extremely low internal resistance of the molybdenum cells, drawing 100 amps generates massive localized heat. If a battery pack utilizes 12 of these cells in series, pulling that kind of current effectively turns the battery pack into a flying space heater.
The battery is chemically and thermally destroying itself in real time to generate that power.
Precisely. The heat builds up so rapidly that if the flight lasted longer than 10 minutes, the battery pack would likely enter thermal runaway,
Which means
melting the solder joints, degrading the solid electrolyte interface layer, and ultimately igniting in midair. It would just catch fire.
But because the mission profile only lasts 5 minutes before the drone intentionally detonates against a tank, the long-term thermal degradation of the battery is completely irrelevant.
They run the battery at its absolute thermal breaking point to extract maximum torque for the shortest possible duration.
That brute force, high-amperage torque gives the Mammoth the acceleration to dive on targets before they can react. But operating a fast, heavy kinetic weapon via a first-person view headset requires an incredibly stable, high-bandwidth radio link to the pilot, right?
Yes, the pilot needs to see where they're going.
So what happens during the terminal phase of the dive if the enemy activates localized electronic warfare jammers and completely severs the pilot's video feed?
That loss of signal in the final seconds is the primary vulnerability of FPV platforms. However, the engineering data reveals a rapid evolution to counter this. We are seeing the integration of lightweight edged AI computing modules directly onto the flight controllers of these heavy FPVs.
Similar to the NVIDIA processors utilizing instantaneous torque on the Lancet.
Exactly. These edge AI systems are designed to bridge the gap when human control is lost. The architecture shifts from manual pilot control to autonomous visual odometry.
So the drone finishes the attack itself.
Right. If the pilot maneuvers the Mammoth into the terminal dive and the radio control link is jammed, the onboard AI instantly takes over. Utilizing sensor fusion and real-time computer vision, the flight controller locks onto the visual signature of the target.
And it just continuously calculates the closure rate.
Yes, and adjusts the 4 motors autonomously, completing the strike with pinpoint accuracy even in a completely GPS-denied and radio-jammed environment.
Wow. So synthesizing this entire stack of sources, we have traced a fascinating evolutionary path today. We started with the Shahed, utilizing the naturally balanced geometry of a boxer engine to suppress vibration and allow cheap IMUs to navigate thousands of kilometers, leveraging raw, loud distance for economic saturation.
We then observed the Orlan 10, capitalizing on the scavenging efficiency of the 4-stroke thermodynamic cycle to sip fuel, converting that mechanical energy into persistent electrical power to keep jamming arrays active for 16 hours.
We analyzed the Lancet 3, weaponizing the pure sine waves of FOC algorithms and the instant 0 RPM torque of brushless motors to create a thermally invisible, hyper-agile interceptor.
We examined the Raybird, pushing the boundaries of electrochemistry by compressing hydrogen at 300 bar and utilizing DC-DC converters to balance the persistent efficiency of a fuel cell with the violent energy buffer of a LiPo battery.
And finally, we look at the Mammoth, intentionally pushing monocell lithium-ion chemistry to the absolute edge of thermal runaway to generate the 100-amp bursts necessary to smash armor at close range.
The overriding thesis across all these platforms is absolute clarity of purpose. The power architecture is not just a component of the drone. The power architecture is the tactical mission.
Right.
The laws of thermodynamics and chemistry dictate exactly what a platform can and cannot do on the battlefield.
It is the ultimate exercise in uncompromising design. But before we conclude, I want to leave you listening with a final, highly provocative concept detailed in the very margins of these engineering sources.
This is where it gets a bit sci-fi, but it's very real.
It builds on everything we've discussed regarding specific, specialized power plans, and it points to a terrifying evolution in how these machines will be deployed.
The concept is cross-domain synergy, heavily reliant on a framework known as manned-unmanned teaming, or MUMT.
The sources indicate that the future of UAV engineering isn't just focused on inventing lighter batteries or more efficient combustion cylinders. The next major leap is in software and standardization, specifically highlighting the integration of standardized communication protocols across all platforms, like drone can.
Right, because currently these power architectures operate in isolation. A Shaheed flies its mission, a Lancet flies its mission. They don't talk.
Right.
But standardized protocols allow these vastly different, highly specialized platforms to dynamically communicate with each other in real time, operating as a unified, autonomous network.
So imagine the tactical scenario this enables. A commander launches a swarm consisting of multiple different platforms. The loud, gas-guzzling Shaheeds arrive first, utilizing their massive range to act as high-visibility decoys, intentionally drawing the attention of enemy radar.
And as the enemy radar illuminates the Shaheeds automatically transmit those radar coordinates via the drone CAN protocol to the silent, pure electric Lancets loitering nearby.
The Lancets, which are remaining thermally and acoustically invisible, utilize their instantaneous torque to dive on the active radar dishes.
Simultaneously, the Orlan 10, orbiting high above utilizing its 16-hour four-stroke endurance, provides continuous broad-spectrum jamming and data relay, linking the aerial platforms directly to heavy, electric, ground-based FPVs waiting in the tree line.
The physical limitations of each power plant, the loud distance of gas, the silent precision of electric, the heavy loiter of hybrid, no longer dictate the limits of a single drone.
No, the engine type simply defines that drone's specific role as a node within a larger autonomous hive mind. The structural and thermodynamic boundaries of the hardware become the defined parameters for the AI software network directing the swarm.
It envisions a multi-domain robotic ecosystem where human operators are pushed entirely off the front line, managing the overarching network, while the distinct power architectures dynamically interact to solve tactical problems autonomously. It brings us completely full circle.
You do not build a consumer minivan to win a drag race.
Exactly. In the modern theater of uncrewed engineering, you build the exact, uncompromising machine for the exact, uncompromising job, and let the network figure out how to utilize it. Thank you for joining us on this deep dive. Hopefully it helps you look past the superficial headlines and deeply into the thermodynamic realities of the blueprints. Until next time.